The next gas law we're going to learn about is something called Dalton's law of partial pressures. And this is by far the easiest of all the gas laws that we will be studying in this unit. Basically, you can see at the top of your screen, it says that the total pressure is equal to all of the pressures of each of the gases in that total, in that mixture of gases combined. Another way to say that is you add up all the individual pressures from each of the gases, and when you add them up, guess what? That's the total. That's pretty much it. So, for example, number one, yeah, that's it. Number one, a metal tank contains three gases. We have oxygen, helium, and nitrogen. If the partial pressures of the three gases in the tank are 35 atmospheres of oxygen, 5 atmospheres of nitrogen, and 25 atmospheres of helium, what is the total pressure? Yes, that really is a question in chemistry. So, can we do this? Let's see. We have 35 atmospheres. We have 5 atmospheres and we have 25 atmospheres. What could possibly be the answer? Let's see, that would be 25 plus 5 is 30. That would be 65 atmospheres of gas inside the tank. Yes, that was a real problem in chemistry. All right, number two gets a little bit more complicated. It says blast furnaces give off unpleasant and unhealthy gases. If the total air pressure is 0.99 atm, again, notice they said total, the partial pressure of the carbon dioxide is 0.05 atmospheres, and the partial pressure of the hydrogen sulfide, which is poisonous, 0.02 atmospheres. What is the partial pressure of the remaining air? So basically, this problem, they're giving us the total, and we're missing one of the parts. So to say that another way, basically, we know the total is 0.99 atmospheres, right? And then we know that the carbon dioxide is 0.05 atmospheres. And we also know that the hydrogen sulfide is 0.2 atmospheres. So what we're looking for is what is the remaining amount. So what is the remaining amount? So again, all we have to do here is subtract. So 0.99 minus 0.05 minus 0.02, and the remaining amount of pressure from the air is 0.92 atmospheres. So there we go. So that one is kind of like number one, just going in the opposite direction. That gave us the total, and we were missing one of the partial pressures, given again, the total pressure. Okay, number three, it says a mixture of helium and xenon is 35.5% helium. So we have a mixture of two gases, helium and xenon. 35.5% of that is helium. The total pressure inside the tank is 15.5 atmospheres. So what's the partial pressure of each of the gases in the tank? So basically, if 15.5 atmospheres is our total, I'm going to convert this into a decimal. So I'm going to multiply it by 0.355. Again, all I did is move the decimal spot 2 spots to the left, right? Okay, so that would mean that my helium is going to be 15.5 times 0.355. That gives me 5.5 atmospheres for my helium. And if I know that the total is 15.5, I'm going to go ahead and show you guys the math. 15.5 atmospheres is the total, and I know that 5.5 of that is helium. Well, then guess what is the remaining xenon? That would be 10 atmospheres of xenon. So there's our two answers of our two gases. They again combine to add up to be the total. Okay, so that's how we do Dalton's law of partial pressures if we have a tank or some sort of container with a mixture of gases. To make it just a slight bit more complicated, what we sometimes have is we have gases collected over water. That's a phrase you need to be aware of, collected over water. When we do that, we do a process called water displacement. Basically, you could bubble a gas through a liquid and trap it in the top of a container, like say a test tube or a beaker or something to that effect. You bubble it through the liquid, and then it's trapped up at the top, and it cannot escape. Then we're able to measure the pressure and the volume of the gases trapped inside that container. So the way it basically works, again, at the top, it says right here that the barometric pressure, okay, remember a barometer measures air pressure. So the air pressure, barometric pressure, is equal to the pressure of the gas and the water vapor. So this part is new, the water vapor. Where we're going to get the water vapor is right here. This is a chart, again, that you would have to be provided. Obviously, we don't expect you to memorize all this information. We would give this to you on a test. It is not on the form of the chart, even though it probably should be, but we would provide this to you. So again, you just need to know how to use it. So again, to put it in mathematical terms, the total pressure is equal to the pressure of the gas plus the water pressure. Or again, to go work backwards like number 2, if you have the total and you have the water pressure, then you subtract them and you get the partial pressure from the gas itself. All right, all that being said, let's go ahead and try numbers 4 and 5. Okay, number 4, it says that when hydrogen gas, again, here's the key phrase, is collected over water at 20 degrees, the barometric pressure, again, remember, barometric pressure, this is the total. At the time the gas was collected, again, because remember, air pressure fluctuates, right? Fluctuates hour by hour, day by day. So at the time it was collected, it was 756 millimeters of mercury. Okay, again, that's the total, right? Barometric, this is the total. Then we have, again, what is the partial pressure of the hydrogen? So we don't know what our hydrogen is, but we do know what the water pressure is at 20 degrees Celsius. I'm going to look up at the chart. 20 degrees Celsius is right here. That is our water pressure, 17.5 millimeters of mercury. So again, if I'm trying to solve for X, all I need to do is take my total, 756.0, minus 17.5, and I'm going to get my pressure caused by the hydrogen, which is 738.5 millimeters of mercury. Again, that's for the hydrogen. The 17.5 is from the water. Okay, so again, that's you just have to find the pressure from the water in the table, again, only if it's collected over water. So number 5, when oxygen gas is collected over water, again, that means we need to use this table. At 40 degrees, the barometric pressure at the time the gas was collected was 1 atm. So 1 atm. This question is very similar to number 4. It's basically the same thing, isn't it? I need to change that for next year. So what we have here, again, is 40 degrees. 40 degrees is right here. So the water pressure is 55.3. Oh, okay, I do see the change. They did atmospheres. All right, so we have a little bit of a curveball thrown at us. So I'm going to erase all of this because notice I was not careful enough. And notice that all of these are in millimeters of mercury. So we are going to have to convert our atmospheres into millimeters of mercury. So let's do that first. Okay, so if we have 1 atmosphere, I'm going to do a dimensional analysis. I'm going to put atmospheres down here, and I'm going to put millimeters of mercury up here. Oops, Hg. All right, so for every 1 atmosphere, it is 760 millimeters of mercury. Again, that is a constant that's given to you on your formula chart. So if I take 1 times 760 divided by 1, it's going to be 760 millimeters of mercury. So now that we know that, that's the barometric pressure. So that's going to be our total, 760 millimeters of mercury. And again, plus our oxygen pressure, plus our water pressure, 55.3 millimeters of mercury. So X is going to equal our partial pressure from the oxygen. So 760 minus 55.3 gives us the remaining part, which is 704.7 millimeters of mercury. There we go. So that, my friends, is Dalton's law of partial pressures. Again, you just add up the partial pressures to equal a total. If it says anything about being collected over water, then you need to use this table because the partial pressures of all the gas plus the pressure of the water that is contained or captured on top of would equal the barometric pressure at the time it was collected. Okay, again, as always, thank you guys for watching.